Okay, as promised, I would work through the problems. Again, this is the optics test, and it is the test that began at 10:30. And so it's a little different than the 8 o'clock one. Actually, it's quite a bit different. I was trying to make the level of difficulty the same and ended up curving it so that the averages will come out to be the same. But let's run through these. Number one is right out of chapter 35, where you have this prism here. And the light comes in, and the first thing is really not a calculation, although I'll put Snell's law down here. That's kind of the foundation of this problem, it's Snell's law. But we know the easy case, that is if it goes straight in along the normal, both sides of the beam hit exactly at the same time and there won't be any bending going on. So that part of it will just go straight through. You could even run through the math and put in 0 degrees here, and the only answer is if you have 0 degrees there. So it just goes straight through. And if you want to do the math, fine. But I didn't think the math was really required for that. Now, in this case, they say this angle up here is 55, which makes this 35, which then when you draw a normal, we're talking about an angle here of 55 degrees. And maybe this first step here is maybe the tricky part. If you put in 55 degrees here, you'll see there is no solution. In other words, you're greater than the critical angle. And in fact, the critical angle, if you do this what is this material? 1.6 is the index. And if we say, okay, we're going to be at the critical angle, we're going to go into air, and it's going to go at 90 degrees, we get a critical angle of 38.7. So I don't know if you want to calculate it, the critical angle exactly. I just did, or just put it into here to see what angle, and you're going to see no solution. And what that means then is it completely reflects. And so that tells us this angle here is 55 and this angle here is 35. And so if I draw a normal here, and my 35 gets kind of crunched, but looking then at maybe this triangle, I'll blow it up. So the beam's coming down this way. I've got the hypotenuse of the prism here. I've got a vertical line here, and this 35 is supposed to be up here, but you can see that this would be then 90 plus the 35, so this is 125. And if you add those two together, you're already at 160, and so that means this angle coming down is 20 degrees. And so now my input angle is 20 degrees. So this would be 1.6 times the sine of 20 degrees here. Goes into air, and then I can solve for what angle does it come out. And at least I know it bends away from the normal. So it's going to be something greater than 20 degrees. And if you run through the math here, you get 33.2 degrees. And so there's the first one. And hopefully it was pretty straightforward. A couple of you struggled on it. But that was the idea, just right out of 35, just a Snell's law. Really, you only have to calculate it once. It's right here, but there is the whole idea of remembering here and here also. All right, well, let's move to number 2 then. Number 2 has 2 parts. The first part, and the second part's just kind of tedious and long, but hopefully straightforward. But I'll start with the first part here, because the first part then just says this: how tall is the image of the arrowhead as seen by the person? So it bounces off the mirror, and so 1 over P plus 1 over Q equals 1 over F. And so this first part is we are 45 centimeters away. Let me just check that up, right? 45 centimeters from a concave mirror that has a radius of 30. So to figure out where the image is, I need to put the focal length. And the thing to remember is the focal length is half the radius. So the radius says 30, so this would be a 15. So with a focal length of 15 and an object distance of 45, I would calculate Q at 22.5. I would then calculate a magnification of minus Q over P. That would be minus 22.5 over 45. And so that's a negative 1/2. And so the height then of the image would be the magnification, which is again negative 1/2, times its original height, which let me just double check here. I think it said 4. Oh yeah, 4 centimeter tall, so 4. And so we're going to get a negative 2 centimeters. So A, is saying how far from the mirror. Well, there it is, 22.5. Let's see, what does it say? What direction does it point? So it would be upside down. That's what the negative magnification would tell me. And what direction does the arrowhead point? How far from the mirror? Okay, and I guess that's it for part A. Part B is the same logic. Maybe a little tedious because what we have is we have this arrowhead here, and we are going to then place, and so we still have the mirror, but we are going to place a convex lens that has a focal length of 15 also, that is placed at 12 from the mirror. And so the tedious part of this is right here, where the light's going to go through the lens first and then hit the mirror. So we aren't going to be able to use anything from A. We can't use this 45. In fact, now that we just learned that this is 12 and this is would make this 33, we could say 1 over P plus 1 over Q equals 1 over F. And if we put in our P now of 33, so we're going to hit the lens first. We can find out where the image is from the lens, and here's my 15. I get a Q then, if we run through this math, of 27.5. Now, 27.5 is way in the heck over here. So if I was, didn't have this mirror, it would form an image right there, which then is what makes then the second part of this not only tedious, but maybe a little bit hard, because the object distance for the second optical element, which in this case would be the mirror, would now be this distance. How far is that? Now, we just calculated this 27.5, so that means this right here is 27.5. So if I take off a 12 from it, we're looking at a 15.5. But, there's the hard part, negative, because it's virtual. We actually put the mirror here before we get to before the image is formed. So when we go to calculate then the image distance from the concave mirror, and so again, notice I used a focal length of 15 for the concave mirror, I get a 7.65 centimeters. And notice it's positive. So in other words, the light would be coming in, and without this mirror, it would have focused right here, but then it bounces off and maybe forms right about here somewhere. The 7.65 positive, and for the mirror it would be on this side. And then, again, a little tedious, because then we got to go through the lens again. This time we're going out this way, because there's somebody standing over here, and the light gets then affected really 3 times, going into the lens, then bouncing off the mirror, then going through the lens a second time the other direction before it goes into the eye of this person. So this right here, which is the image of the second one, that's the image of the mirror, is now going to become the object of the lens again. And so when I go 1 over P plus 1 over Q equals 1 over F, my P then would be this distance, which this is only a 4.38, given that this distance right here is the 7.65 2. So when I add those two together, I get the 12. So this is 1 over 4.38 plus 1 over Q, and still would have a focal length of 15, of course, because remember, the focal length depends up, it doesn't matter which way the light's going. Focal length is a combination of both curvatures. So going left to right or right to left, the focal length is still the same. And so Q then comes out to be a negative 16.17. Now, making kind of a messy picture here, but negative, so if the light's going this way, the negative would represent light over here somewhere. And so it would be 16.17, that direction. So if the first part of this question is how far is it from the mirror, then I would take the 12 and subtract off the 6.17 and get the 5.83 centimeters. So that's how far it is from the mirror here. And then when I go to figure out whether it's upside down or how big it is, maybe I'll just move this. Maybe I'll fold it and leave it kind of so you can still see it. But I need to do the magnification. And so the total magnification is really the effect of all three of them. And so the first magnification would be minus its Q, which we said is 27.5, over its P, which is 33. So there's the first magnification. The second one then would be a minus 7.62 over its negative 15.5. So two negatives there make a positive. And then the third magnification is the negative of the negative 6.17 over its p-value of 4.38. And so that's a positive value also. So I've got a negative, a positive, and a negative. And so overall it's negative. So it's going to be upside down. And when you put all these numbers here together, we get an overall magnification of 0.577. And so to finish this, what is the height of the image? We'll take the total magnification times its original height. So that's negative 0.577. And times its original height. What was the original height of this crazy thing? It was 4, right? 4 centimeters. We're going to get a negative 2.31 centimeters. So that's the, like I said, part B. Hopefully not hard, but a little tedious because we've got to do there it is, the same thing 3 times here. And then the magnification, same thing 3 times. So A and B are kind of the same. A is just do it one time, but B is kind of that harder question of, okay, can you, what do you do? We have a second, a third, a fourth, a fifth, a sixth, a seventh, an eighth, And some of these 7-lens systems are really neat. The 7 works out really well because, well, I guess beyond the scopes of this optics class, but the focal length we talk about is actually a little different for each different color. And so it's kind of nice to put a combination of different lenses with different focal lengths for the different colors, and some of the dispersion patterns exactly match. And so after 7 lenses, you get an overall focal length the same for every color. And that can make a really good quality camera that way. But that's for another day and another time. Let's try number 3. Number 3 is supposed to be an easy one. It's just really kind of a plug and chug. It's probably the easiest one on this test and the other test too. The equation's straightforward. We learned here that the intensity anywhere on the screen would be the intensity at the center of the screen. And then there would be a we decrease intensity as we move from the center because of diffraction. And in addition to that, there would be a change in the intensity according to the interference or the Young's double slit part of the experiment. And the stuff that goes in here and here, the same thing, is the pi times the A, and I'll say sine theta, but let me just write that as y over L, and then over lambda. And the stuff that goes here, so you notice this has to do with the A, this is the diffraction. And then this is the pi d, and I'll say sine theta, but I'll write it like over here, y over L, and then a lambda. So this is just a straight plug and chug. You know all these numbers. The problem gives you that number, and it gives you that number, and it gives you that number. This, let's see, what did they give you down the center? This is 15, okay. They're saying that find it at a position y of 1.5 centimeters, okay. The size of the slit, double slit separated. So this right here is the 0.06 millimeters. The wavelength here is 410 nanometers. L, the distance to the screen, is 1.15 meters. Of course, you know what pi is, so we can put those in. And the only thing would be here, new would be this D. This is 0.2 millimeters. And so the same Y and same L and same wavelength, same pi. Anyways, this is just plug and chug. So put that into here, put that into there, and you're going to get an intensity of 0.00577 watts per square meter. That's all. So this is the energy because of diffraction. This is the energy because of interference. So that's why I said this is probably the easiest one on any of the tests. It's just, hey, just put in the numbers, you got it. All right, well, number 4 then. Number 4 is this thin film here. Now we have an oil droplet. And so we've got this kind of this mound up here. And so just to kind of review the thin film stuff, light would bounce off of here and bounce off of here. And so if we said this had a thickness of t, we would say that if 2t is an integer of wavelength in the film, we would expect to get a maximum on reflection because we'd have constructive interference. Now, that, of course, ignores any phase changes. And in our case, we're in the air and we're sitting on water and we have oil 1.15. So I like to put a little circle. There's a phase change there, but there's also a phase change there. And so the interference really is the difference between those two. And since they both have a phase change, we could just kind of ignore it also and say, well, neither one had, because it's a comparison. So the only thing different about them, since they both have a phase change, is that extra distance of 2t, that this one here goes down and back. So we don't have to worry about phase changes is another way of saying the same thing. They both undergo a phase change. So the difference is path difference. I like to use the symbol delta for that. So the lowercase delta. And so this 2t, an integer number of wavelengths, is where you'd get your maximums on reflections. And this problem does talk about reflected light, and it does talk about maximums. So this is really the working formula for this one. The transmitted one's a little bit harder, so that's what's on the other test. But the this right here is showing then that, for example, m equaling 0 would correspond to a thickness of 0. So down here, you have just a microscopic distance, not enough to really get them out of phase, but the two add up constructively. So the very edge of this would be bright, and it says you see 12 of them. So it would go bright, dark, dark, and so eventually in the center there, because I guess you got to kind of think of this also in 2 dimensions, looking down on a droplet. This would be the same as that. It would be one big circle around it. Another big circle, and another big circle, another big circle. Okay, but the point is, to get 12 of them, we really only count to 11, and that's kind of important here. Because to get then the thickness, T, I would put in M equal to 11. And then I can move the 2 over to here. But I would also then say that I have this wavelength, and what they say the wavelength was 520 nanometers. And the index that this is all taking place is in the oil, so make sure you use the index for the oil. And so this comes out to be a thickness then of 2,487 nanometers. Now, number B, or letter B here, was not a very good phrased question, so I apologize, and I was very liberal with this. I really didn't do much of anything. There's so many things you could say. Just said, what would a fish that is in the water see at the thickest part? And what I was after in this is that these would reverse roles. And so at the thickest part, if you're getting constructive interference because of conservation of energy, then transmitted light would be exactly the opposite. So instead of getting bright, you would get dark. And so glad many of you saw that. This was what I was after, is a fish would really see the same pattern, but instead of brights they would see dark. And so somebody on the outside would see these rings of bright, dark, and somebody underwater, a fish underwater, would see the same set of rings, bright, dark, but they would be the opposite. That is, where the bright ones are for reflection would be the dark spots for transmitted. So that's kind of what I was after. But there's a lot of other things the fish would see, and so there was all kinds of answers that could have been. So I just go, yeah, that makes sense, given the question. But like I said, that's kind of what I was after. Where it gets a little more interesting is when you warm it until the thickest part turns from bright to dark. Okay, so that's where the other equation came. The dark one then would be 2t equals an integer and a half wavelengths. This is where you would get the minimums when you're talking about the reflected light. All right, so I'm going to use this equation for part C because we're talking about the reflected light. And at the thickest part, we were already at 11. And so I'm going to say then that what ended up happening is it got a little thicker because of the thermal expansion. You're warming it up, it's getting a little thicker. And so this thickness increases, and so we get to 11.5. Instead of a thickness of 11 wavelengths, we get to 11.5 wavelengths. And so if we put in our 11.5, I'll move the 2 over, and we still have our 520 nanometers, and divided by the index that it's in, the 1.15, we would get then a little greater thickness of 2,600 nanometers. And so that's what number 4 was about. That thin film interference, our wave optics. And then on to the last one here, number 5. Number 5 starts off easy. And believe it or not, B is actually pretty easy. It just may not seem it at first. This is going to ask you to kind of put two things together from the 2 different chapters, the geometric ones in chapter 36 and our diffraction here in chapter 38. but one step at a time here. And so what I hope you learned here in chapter 38 is that the light would spread out. It would make an intensity pattern that would look something like this. It would be very bright in the center and then kind of fade away. The pattern looked like this, the intensity at the center, and then it was this sine squared over squared. In fact, it goes back to this in number 3. This is a sinc function. Actually, I guess a sinc function squared. And that's the full equation. So we don't have to go all the way back to something as complicated as the equation for number 3. But we learned that the dark places, that is where you would get no light heading, had these integer multiples of it. That's where this was. And so this was m equals to 1, and m equal to 2, and m equal to 3. And most of the light would be really intense in here. And so something like 90% of the energy is in between this m equal 1 and m equal negative 1 here. And that's really what we mean by the size of the spot here, from here to here. These would have a little bit of light, but for the most part you would ignore them because this is 90% of the energy here. And so if you then just kind of solve this and say, well, sine theta, and we're talking about the first dark spot, so I'll put m equal to 1 and I'll have a lambda over an a. That would be your equation of the angle that it would make as it spreads out. And then that's kind of your angle there. You might approximate this and just say, well, that's theta. But you then might also approximate the theta as saying this is y over this length, and the length to the screen we usually put an L. And so this would be the y. And then, of course, maybe an added point here is to say the size on the screen would be a 2y. And so if I multiply by 2 and multiply by 2 and then bring the L to the other side, I get a 2, a lambda, an L over a. And so there would be the size on the screen. And so I've got the 2. The L, they said, is 1.8 meters. That's the L. The lambda is the 600 nanometers. And the size of the slit is the 90 micrometers. And so 0.024 meters would be the size on the screen. And believe it or not, B really isn't much different. It really does kind of tie with our optics. Maybe we'll go all the way back to number 2. But the logic is if you put a lens or anything, then the lens will make an image. And so in this bag, number 2, the image was right here. This image then becomes the object for the next optical piece here. So if our final question is on the screen, and you have what I'd call a legitimate opening here of 90 micrometers, and you put a lens, and it's a concave lens, then what does the screen then really perceive? It doesn't perceive the true opening like it did in part A, but it perceives what we get from the image. And as the light goes through, we learned that this kind of lens is kind of the boring one. It always made a virtual image, and so the opening would look a little closer. And it always made things smaller, so it would make it a little smaller. And so if we think about this as the image, then we can just say that the size on the screen is the same thing. It is 2 times the wavelength times the L times the A. However, the L is a little different. The L is not really the full distance all the way back, which was the 1.8 meters. It is the distance from where the light now appears to be coming from after it went through here. In other words, the real slit with the lens together are equivalent to the light coming from right here. That's why we called it an image. And so if the light was coming from right here, what would you see on the screen? So this is our L. Maybe I'll call it L prime to point out that this is now the L we would see. And it, of course, would magnify it, or in this case, reduce it. So maybe I should say there is an A prime. And so that's what I mean. B is really the same as A. It's just, you got to realize this part about our geometric optics. So if I go ahead and then put something like a 1 over P plus a 1 over Q equals 1 over F, and I say here that the lens is, and I think it was 30, let me just check here, it's 30 centimeters from the slit. Yeah, so from here to here is this 30. Where is the image? Given that the focal length is 40, and I'd have to watch my sign convention, that's a negative 40. But if I put in my negative 40 then and do a calculation for Q, I get about a negative 17. And so from the lens back to here is 17. And that's centimeters. And so keep in mind then that this right here would be 150 centimeters, because remember the whole thing is supposed to be 1.8 meters as we did earlier. It's 180 centimeters. And so really what the screen is seeing is a slit that is 150 and 17 more. So I'll put in the 600 nanometers, but this L then would be 1.67 meters. That's the real key, is how far is that? And then the A is the, now the size of this, and so I'll call it the A prime. It's how much has it been magnified times the original A. And now the magnification is negative of the negative Q over a P, and the original size we said was 90 times 10 to the minus 6. So the size of this is a little smaller. Now it's down to 51 micrometers, but that's what would go right here then, 51 micrometers. And so the size of the screen, or on the screen, would be 0.039 meters. So, like I said, this B looks like it might be kind of hard, but it's hopefully not now that you see. It's just, hey, throw the lens in there, and, just like we would do any 2 or 3 or 4 or 5 optical elements, the image from the first becomes the object from a second one. And so you can then say, from the screen's perspective, you can get rid of the lens and get rid of the original opening, because you can now just treat the light as coming from the image. That's the effects of this lens on that slit, that opening. Well, hope that helped.